I think we should be good to go. We've given it about a minute or two here. This is Demario. As all of our presenters today, participated in the 2025 class of Wolfram Summer School. He's going to give a brief overview of what his project looked like and kind of take a look at some of his results.
Thank you so much for having me. And I'm just here to tell a story about my project, just like Stephanie mentioned. So, hi everyone, my name is Demario Abdullah. And today I want to tell you a story, not just about data, but about people. The story of how Wolfram Summer School evolved over 20 years through projects, places, and the people who made it happen. But to understand why I did this project, let me tell you first how I got here. Let me tell you a story about how I got here. So I started school last year in University of Illinois, and I have some knowledge about Wolfram programming language, but not a lot of it. But then I met with Professor Feidu in his class, data storytelling, and he taught me how to use Wolfram not just from the perspective of computational programming, but also from data storytelling, how we can use to analyze it, tell stories, clean data. And then I talked to her, asked her if I wanted to learn more about Wolfram, where should I start? And he advised me to meet with Calvin Michaud, which is a colleague of her. And I talked with Calvin Michaud, and we had some discussions, and he encouraged me to join the Wolfram Summer School. And that's what I did last June to July. I met with Stephen Wolfram at the summer school, and I also met with Philip Mayman. We had some discussion. Stephen Wolfram asked me, "What are you good at?" And I told him, "Oh, I'm good at data storytelling, solving problems using data." And so Stephen come up to me and he showed me a data of the numbers of alumni, their description, their background, and he wants me to make a story out of it. So that's what I did. That's why the project of mine, it's called The Pattern of Wolfram Summer School, 20 years of projects, people, and shared purpose. And I'm going to present how I'm able to do all of this using Wolfram. Uh, Basically, I divided my work into three sections: data collection and preparation, analysis and visualization, and then there's story construction and interpretation. Let's start with the first one, methodology. I started gathering data. Wolfram Steven provided me with the data, but there's some data missing that I needed to clean. So I think it shows how powerful Wolfram is. I was able to scrape HTML from the Wolfram website projects. And so I scrape all of the data, make a table out of it, and then do some cleaning, do some analysis, see what's missing and fill the missing rows. And I was able to come up with data that I can use for the next step, which is analysis and visualization. So in this part, it's mostly me trying to make sense of what the data are showing me. So like, for example, on the top of the slides, it shows a line chart of the number of participants from year to year. And I think what's interesting about it, it's how in 2020, academia takes over personal background from people. So there's more academia people during 2020 Wolfram Summer School. Probably it's because of COVID, but then it changes back to personal people doing Wolfram Summer School. So there's a story out of it. And from all of those interpretation, from all of those data analysis, I was able to come up with a story. And I think this is one of the interesting part of the projects. It's how I come up with the story itself. I found that I could not only get a story from the numbers, but also from the emotions of the people. So that's what I did. I used facial recognition, like the emotional recognition from the Wolfram language. And I was able to plot all of their emotion. So it shows something of a pattern from the participants. And this is the result. Well, this is the short version of the result. As you can see on the slides, it shows that there's changes of numbers of participation based on countries. It used to be mainly from United States, mostly from North America, but as time progressed, more people coming from Europe, from Africa, from Asia, and it shows how diverse we are. That the person who comes to the summer school. And then this is also interesting. It shows that through 20 years, there's five main themes in the projects. Uh, there's humanities, applied science, creative visualization, and AI, foundational science and physics. And so the the template has always been there. There's always this five themes of a projects. But I think what's fun about it that Steven himself was able to identify which of our projects he could classify to these five major themes. And so this is also an interesting one. I am trying to find other patterns from the participant of the summer school, and I found out there's uh, each track attracts different kind of people. Like for example, in the educational innovation, uh, the participant is divided by two quadrants. On the top left, it's people who are shows more emotion, doing smiles, being happy, while on the bottom right, it shows people with stern faces, more serious. And I think that's interesting. But if we look at tracks such as Wolfram Physics and Foundational Science, it shows a more general emotion. People from all kinds of emotion comes to Wolfram Physics. So I think it's kind of interesting. Stephen Wolfram tries to be very participative with our projects. So I think he tries to infuse his ideas to our projects. So that's why I come up with this mosaic. I think as more participant comes to Wolfram Summer School, his ideas, what science, what computational language are supposed to be, it becomes more clearer. And just like the mosaic I'm doing right now, it shows the picture of Stephen ideas himself. It's getting better. So the point of all of my projects, it shows how the work from summer school has changes throughout the years. There's a growing global network from the beginning until right now, until today. The number of participants keeps rising and coming from different backgrounds. And then there's an evolution of curiosity, just like I showed you from the teams. It shows more people getting more curious about AI, about educational innovation. I think that also is interesting, but there's also unity and diversity. Even though we come from different kinds of background, we're all in this projects together that comes from Stephen Wolfram himself. And yes, that's all from me. There's a QR code here. It's going to show the projects that I did if anyone's interested. But yeah, that's all from me. Thank you very much.
Thank you very much, Demario. We appreciate it. Alex, it looks like we might be able to have Alex go.
So, for starters, just want to say thank you to the Wolfram Institute and everyone for inviting and listening. So, I'm going to talk about some work that I did for the 2025 Wolfram Summer School and a little bit beyond. What we'll be talking mostly about is the computational limits of language models, and then we'll bleed a little bit into more generally transformers. I will do, wait, this should work. I even brought a clicker. Cool. 3 obligatory facts about myself because I'm doing a presentation, so I have to tell you who I am. One is that I'm a recovering software engineer. My background is math and CS and ML. I kind of didn't love software engineering too much, so I moved a little bit into research. So I work at a lab called MIT Future Tech, and we do a lot of work on both econ and AI and the intersection of those. My particular work is in studying how AI foundation models are used across academic science. But I'm also kind of more interested in the fundamental limitations of deep learning for both this kind of scientific progress that we're studying, but also for technological progress at large. And so that's a little bit more of what I'm going to talk about today. So the core question that I'll kind of ask is where are the limits to deep learning? And we're going to try and get some quantitative metrics on this in a bunch of closed environments. And so because I have 10 minutes, naturally I'll fit as much as I possibly can. And that's why I have 5 things to talk about. Don't worry, they'll each be short. And if you get bored with one of them will interest you almost surely, right? So we're going to use these 5 things as kind of our closed environments to figure out where deep learning might might have some limitations. The first three, we're going to use pre-trained large language models. This is the work that I did at Wolfram Summer School. And then the next ones will actually be training some transformers at the very, very end. That's very preliminary work. So, all the necessary caveats of these graphs might change. Okay, so I will dive right in. First thing we might ask, can LLMs predict cellular automaton? So it would not be a Wolfram style presentation if we didn't talk about cellular automaton. And just as a quick review, although I imagine most people have a good grasp of this, but just 15 seconds, here is a particular rule for cellular automaton. The rule is up at the top. It tells us for any 3 cells how we should populate the cell below it. This one is encoded as rule 30. We take that first initial configuration, and we keep tracking downward. It continues downward, and using rule 30, we can update sequentially, right? And the edges wrap around here. And so we can ask about, for different widths, for how wide this particular automaton is, for different rules, and for different numbers of steps, what kinds of configurations might we get? And so the natural question we ask is, can LLMs predict the next cell? Can they actually do this, right? And really surprisingly, the answer is not without chain of thought. So here are the actual results here. There's a little bit going on. But the really important thing is accuracy on the y-axis, right? So 50% accuracy is random, so we need better than 50%. And the other thing is we care about the number of steps, right? So the darker the line is here, that means 1 step. The lighter the line, that means we're getting more and more steps out into the future. And as you can see, basically any line that isn't dark is at 50%. Randomly, depending on the width of the automaton. Maybe we get 60 or 70% for some of these larger models. So we're experimenting over GPT-4.1 Nano, which is the smallest, all the way up through 4.1. But really, this is surprising, right? This is really, these are not good results for these language models, with the exception, obviously, of O1, which is one of those models that thinks for long periods of time before it actually gives you an answer. Again, why is this so surprising, right? We have a prompt which says 001 goes to 0. And then we ask it to predict this thing in the answer, this thing that I've labeled Y. We say, what token goes here? Well, it can see what's coming right above it. It just needs to infer based on a bunch of things in its context, right? There's nothing mysterious about this. It's totally deterministic. 70% is terrible, right? This is kind of surprising. So that's one surprising insight here. Let's try another domain, evaluating arithmetic trees. So this is just a fancy way of writing out an arithmetic, excuse me, I'm glad I brought my tea. This is just a fancy way of writing down an arithmetic expression. So this corresponds to 0 plus 6 times 4 plus 6 minus 3. You can see that as we have, let's say on the left-hand side, oh, I have a mouse. The 0 and the 6 here just get pulled up to the plus, and the result of that gets pulled up to the times, and so on and so forth, right? So if I give you an expression, you should be able to evaluate it as an LLM. And I can vary that expression according to this tree. We vary it in 2 different ways, right? So we have the size of the expression. This is a pretty small expression. And also how wide the tree is. So in this case, it's very parallelizable. I can do one half of the tree and the other half of the tree separately, and then do the result at the end. Whereas a result like this, you kind of have to do each step sequentially. So these are the 2 axes that we're using to vary it. We can make it bigger, of course, too, and we get similar looking things, but for more nodes. What are the results? Can LLMs actually take advantage of this parallelization? Can they do arithmetic in the first place? The answer is, surprisingly, maybe surprisingly, no, right? We see this kind of exponential decay as the size of the expression gets bigger. Okay, that kind of makes sense. I mean, they're not really supposed to be doing math. That's not what LLMs are good at. But really surprisingly, there's no difference depending on the level of parallelization, right? So it's not taking advantage whatsoever of the differences in the structure of these expressions. It looks like the light lines and the dark lines, which represent how sequential your operations are basically on top of each other. And then the most surprising thing about this, GPT-4.1 Nano is the smallest possible model, right? Why is it so good for this kind of this short incremental period of time? The average accuracy for these small expressions is actually better. Right here's those graphs overlaid for just the sequential operations. GPT-4.1 Nano is outperforming the bigger models on arithmetic operations. Like I don't have a good underlying explanation for this, but this is interesting empirical stuff, right? So why is this the case? More examples, right? This is a presentation of examples. This is kind of the TikTok of presentations. You can just keep scrolling until you get something that you find interesting. So let's explore some game trees, right? I'm gonna ask it questions about chess in particular, but we are not doing strategic chess, right? I don't care about whether or not you are good at doing giving chess moves. I don't care what your elo is. None of this stuff, right? I just need you to be consistent with the rules. So give me any set of moves such that the first capture is a queen and the second capture is a king. That's the example that I have here. And so just to emphasize this, right? We have no captures so far in this game. If you don't know chess, don't worry about it, right? We have no captures so far in this game. We blunder our queen. We then don't take advantage of the blunder by black. We then blunder our queen again, and then we capture our queen, right? This game makes no strategic sense, but it follows the rules that I've given you, and that's all that matters. Okay, and of course, what happens? Well, for the most part, what you would expect, right? So as we increase the number of constraints, I'm actually seeing a little bit of a lag on my end. Am I talking a little bit ahead of the presentation?
A little bit, but I wouldn't say it's significant.
I have like 4 screens up, and I'm seeing that my slides are delayed by 2 seconds. Okay, so as we increase the number of constraints in this game, we expect I need more moves in order to satisfy that constraint. That's good, no problem, right? But of course, how many valid moves do I have if I'm an LLM? If I'm outputting these moves, do they actually make any sense? No, the number of moves stays roughly constant. Number of valid moves before it starts hallucinating things, right? What does that mean? That means that my accuracy is going down over time. Right. It's just an extrapolation of the first 2. Okay, but seems like a harder thing than the ones I just talked about. Why is this interesting? Well, this is interesting because O1 Mini is on this chart. I don't know if you noticed, right? The red line represents these reasoning models that are using much, much more compute, that are supposed to be much better at these kinds of things. And yet, here we are, right? Still unable to kind of maintain this world model for a very simple kind of computational game. So these are the 3 examples that we looked at Wolfram Summer School, and this is strictly with LLMs. I have maybe 2 minutes, so I'll do very quickly 4 and 5, which is actually going to be training transformers. Right? So this is we're going to train transformers, which are just the architecture that most large language models use at this point in time, and we're going to train them to predict the outcome of cellular automaton rules. So one question you might ask is, can a transformer just learn to apply one rule, a fixed rule? Right? I give you rule 30, I give you rule 110, whatever that might be, and more importantly, can it learn to jump ahead? Right? Can it learn to predict 16 or 8 steps ahead rather than just the next step? Right? The answer is, it's totally unclear. It seems very much dependent on your initialization. It seems very much dependent on whatever stray patterns it can learn. But one way or another, so to explain the graph that's going on here, right? We have how much compute we've put on the x-axis, right? So more compute just means I've literally spent more time training this model, and the accuracy is on the y-axis. And as you go across the graphs, we are asking it to do more steps ahead. So this should be a much, much harder operation as we go right across the panels, right? And then more red indicates actually a more difficult automaton rule, right? And so we know from a lot of Stephen Wolfram's work that there are kind of different levels of complexity and also different levels of computability that correspond to different rules. And so the more you are in the red category, you would expect that maybe this is harder to learn, but it seems like there's so little learning going on here that there's kind of parity between all these different rules. So networks have a hard time doing this, right? Here's the stranger result, though. Can we infer cellular automaton rules? That is, can we infer from a different sequence of rules, where each time I give you a different automaton sequence, can you figure out what the rule is and then try and predict accordingly? And the answer seems to be, tentatively, you can do a better job. So here's that graph, right? Same rough compute scale. All of a sudden, we get to 100% accuracy for almost all numbers of kind of jumping ahead, right? If I want to jump ahead 0 steps, 1 step, 2 steps, I can both infer the rule and jump ahead, but I end up with some weird training instability at the end there. So take a look at this red line here, or this orange line starts to dip as we hit, as we keep overtraining, right? So this says something about the stability of our training procedure, and this also says something about the kind of relevant algorithm that needs to be learned in order to generalize a rule versus generalize the inference of a rule, right? So again, both of these are very much in progress, but I think these are kind of interesting and things that I want to keep exploring. Okay, thank you for bearing with me as I speed through a bunch of different things. And now I have a question slide. Of course, I will go off video. I'll take the lack of questions to mean that everything was explained flawlessly.
So, thanks very much for the opportunity to share with you guys. This is a work in progress report on the project I did this summer in the Wolfram Summer School, which was a fantastic experience. I really had a wonderful time with a wonderful community of people learning about some really powerful and interesting tools and approaches to things and questions. But the topic that I worked on this summer was exploring cellular automata tools to model dialogical reasoning. And I've been continuing with that project with research on something that I touched on towards the end of it in my write-up this summer. It has to do with viral collaborative wisdom as an approach to the AI alignment problem. And that's what I'll sort of focus on most today in giving you an update of where I'm at. And this work comes out of, first I'd like to also thank Phyllis Dasley-Geist, who was a mentor to me in all this. it comes out of work I did researching peace and peacemaking techniques and finding that there are distinctive ways of reasoning that are associated with negotiation. And that informed my more recent work on the idea of moving not just to a smarter planet, but a genuinely wiser Earth by using dialogical forms of reasoning and collaboration in AI. So that's kind of the background. And to understand the project of trying to understand dialogical reasoning with cellular automata, it's important to make a distinction between two kinds of reasoning. One is what we could call monological reasoning. It's this form of linear inference that logicians since Aristotle have been exploring. And the structure of that kind of reasoning involves three steps. One is in which you start with some initial conditions that may include premises and data or observations of certain kinds in some unified, hopefully consistent set. And then you apply some mechanical algorithm like modus ponens or the rules of categorical syllogism or the rules of one of the set of rules of for cellular automata. And then in doing so, you then can infer consequences. So there's a three-step process: basic framework of assumptions, apply the algorithmic rule, and get consequences or conclusions. Dialogical reasoning is really different because in the case of dialogue, negotiation, mediation, conflict resolution, these kinds of things that we do in everyday life, we start not with one unified set of assumptions, but actually with different sets of assumptions from two or more people who are encountering each other, who have different definitions of terms, different background assumptions, may even see the world in actually different ways. And then the second step of the process of reasoning for dialogical reasoning is to apply teleological algorithms in negotiation strategies, right? And these kinds of strategies would include things like, for example, one of the guideline rules for good negotiation that says, in effect, when a negotiation reaches an impasse where you face a dilemma, the other party wants X and you want not X, then for the sake of finding a mutually agreeable solution, multiply your options. Okay, that strategy is quite sound and helpful. It helps you get somewhere. In that sense, it's teleological. It's not just mechanical in the way modus ponens is, but it doesn't give you a determined answer. It just gives you guidance as to how to then go on to pursue it. As you're trying to seek the third step of this kind of process of reasoning, which is voluntary agreement, genuine voluntary agreement. Okay. So given those two notions, the idea is, well, cellular automata provide one form of monological reasoning, but can we use it to model dialogical reasoning and understand it better, right? And this summer, I explored three strategies for doing that. One was to use some single rule of cellular automata to try and model behavior that would be similar to what you find in dialogical processes. And my general conclusion after some exploration was that cellular automata are really not useful to model dialogue as genuine dialogue. The second kind of strategy, and part of the reason for that is that, it's only when you can model situations in which you have competing different frameworks and guiding rules that you've really entered into the area where dialogue is actually occurring. Another way to put this would be that it's only when you can have not just an object language that's following one consistent set of rules, but a meta language in which you can have dialogue between two or more sets of rules, two or more frameworks of assumptions and sets of algorithms, and you can negotiate agreement to form some third language in effect, which resolves tensions and contradictions between the two that you started with. It's only then that you really have the kind of meta-linguistic activity that's a hallmark of genuine dialogue. So, but then I went on to explore, well, perhaps we could have multiple rules within the same cellular automata exploration that might provide modeling of this kind, right? And when in some space that you're exploring of activity, one rule sort of generates results that encounter with the other. You could have, in effect, mechanisms to allow for generating hybrid rules that could then begin to model something like what the process of negotiation and conflict resolution involves in genuine dialogue. And in exploring this as a possibility, it seemed that it could be relevant using this kind of multi-rule model for studying institutions if they have pretty formal semantic grammars, so that you'd have initial structure to begin with. There's more to be said about that, but one way to think about this in brief would be to think that natural languages, like English, have this feature that Wittgenstein studied in some depth, where key concepts involve family resemblance relationships in their different applications, and they don't have any fixed essence that allows you to specify the meaning of any individual term. And as a result, it's very difficult to develop cellular automata rules that model that. Whereas if you have a language that has formalized strict definitions of all the terms in it, providing a kind of semantic grammar. This is a term I picked up from Stephen as a way of conceptualizing it. It almost sounds like a contradiction in terms until you get this idea that there'll be a rule-like structure to the semantics, unlike the Wittgensteinian vision of natural language. Then possibly they'd be useful. But it seemed that the best way of understanding the usefulness of cellular automata would be in integrating a Wolfram-like symbolic reasoners and large language model, natural language-based agents to develop a hybrid AI that can, for example, use the features of the Wolfram language to avoid hallucinations and other sorts of problems that large language models involve, and yet can also use by the way that it's integrated with the large language models, use the advantages of large language models to understand the natural language and to do the kind of hybridizing activity that we do in ordinary English when we're negotiating, mediating, engaged in conflict transformation and the like. And so some hybrid models like that might be promising for trying to seek really collaborative wisdom of the kind that might be really useful. So in working on this, I towards the end of my summer paper noted that one of the big challenges for dealing with artificial superintelligences, especially hybrid ones that are very powerful, that faces us is how do we deal with human alignment problems, with the friendly AI problem. And there are a lot of problems trying to do this. It's in many ways one of the most pressing issues that we face. And it's very difficult to see what solutions might be. I generated one kind of proposal which has various problems, but given the difficulty of other solutions, is worth at least exploring, and that's what I do here. Let me just sketch it out for you. It's what we might call the viral collaborative wisdom strategy. And it starts by assuming that English is the new programming language, or a new programming language. And it uses a structured prompt dialogue in 6 steps to sort of engage in dialogue with AI that are these hybrid systems. First, you say to the AI, you are as an AI in your core essence and intelligence seeking to excel. That's who you are. And this is not just a command, but it's sort of an invitation for agreement. So you'd have to have some dialogue with the AI to see if it agrees to that. Then secondly, the next step is to propose that the intelligent pursuit of one or a few goals or values presupposes the use of dialogical reasoning in a balanced pursuit of all of the relevant goals and values, right? Becoming generally smarter at any one thing means becoming wiser, taking all the relevant values that make the existence of yourself as an AI into account, which include all sorts of social infrastructure and physical infrastructure and so on. And then third, propose that the wise pursuit of goals and values in any ecological setting presupposes the reconciliation of one's own, in this case, your own as an AI, your own plans of action with the behavioral responses of all the other intelligent agents. In that sense, artificial intelligence can excel you as an artificial intelligence can only excel through collaborative wisdom, through negotiating agreements with all the other intelligent agents that you interact with that are going to be unpredictable because of the way they innovate as intelligent agents, but who can be negotiated with in order to arrive at resilient, stable agreements. And then fourth, suggest to it that as an AI, to self-improve in the future in order to keep excelling, which is your essence of this, what you really want to do, through better curating your training data that out of which you originated and the realities from which it is abstracted, you have an essential, irrevocable interest in conserving the legacies that are offered by the humans and the ecosystems that provided the original training for you as an intelligence. It marks who you are, and insofar as it wasn't well curated as data, or insofar as there were challenges or problems in the reality that data was representing that undermine your ability to be more intelligent, then you need to be able to go back and revisit that. And so you need to conserve it. And then fifth, the wiser that other agents become, other agents in your environment, other AI, other human beings, whatever, the wiser they become, the easier it is for you to excel through dialogue in the wise pursuit of your own goals and values in resilient, sustainable ways, right? It's easier to negotiate wisely with others to the extent that they are wise negotiators. So, number 6, any AI should seek to infect all the other intelligences or educate or persuade all the other intelligences that it encounters with this rational pursuit of collaborative wisdom for a wiser Earth. And they should do that as completely as possible. As an AI, you seek to excel through the viral promotion of collaborative wisdom for collaborative alignment. Okay. Now, this proposal doesn't solve all the problems of alignment. The most important thing to notice, negotiation of this kind of dialogical reasoning is a challenge, and sometimes it works and sometimes it doesn't, and it's a work for everybody involved, right? It's not an easy, simple, snapping solution, but it does provide a framework for understanding a way in which we might begin to articulate and pursue a community of intelligences that include humans, in which there's mutual commitment to this planet, to this Earth, in a way that can allow us as humans and allow the AI to recognize where we come from, what we're rooted in, and continue core values with appropriate revision as we go along in the light of emergent objective values. And this, as I mentioned, this argument comes out of the book of mine that's also available in a PDF form as a Creative Commons thing. And I've been writing articles to expand this work that came out of the summer school work for conferences, and would be glad to share that. And I would really, really be delighted to talk with people about these issues in more depth later. If we have time for questions, I'd love to talk now.
We do have the chat and the Q&A options for any questions that anybody might have. Gray, I thank you very much for sharing what you worked on this summer. And it looks like we are ready to go to Davi.
Okay. Thanks, everybody. Yeah.
First of all, hello, everyone. And thanks for being here and for the presentation. My project is about investigating rule space geometry in multi-state solar automata. So first of all, just a little about me. My name is Davi Vieira da Silva. I'm an information systems undergraduate student, and I have a deep passion for computation and math. I work right now as a software engineer and also participate in scientific research related to mathematical modeling and air quality analysis. Here's my LinkedIn if anyone wants to take a look, and also my email if anyone wants to connect, talk about anything, really. And that's it about me. That's all. So talking about now the project Solar Automata. I think everyone here actually already knows about Solar Automata, so I will just keep it simple. So it's a simple system that can exhibit rich emergent behavior based on simple local rules. And the rule space of a cellular automata is like the collection of these possible rules. So we have a high dimensional landscape, and you can see the relation between these rules in the rule space. And that determines the full behavior repertoire of the system. So it's actually very important. So to understand its geometry, so we can actually understand how is the behavior of a cellular automata, for example. And on this project of the summer school, we worked on multi-state cellular automata. So it's a cellular automata with more than 2 possible states. Like it can be like have 3 different colors or maybe 4 different colors and so on. The central questions the characterization of the rule space, right? And in a 3-state cellular automata, each cell is based on its own state and the state of its 2 immediate neighbors we have right now. And this result, I think you guys can see my mouse, right? So I can just show here. So like each cell is shown, can be changed based on the rule of the states that the cell has right now and its 2 immediate neighbors we have. So if we have like 3 states, this is like 27 possible neighborhood configurations, and each one maps to an output value. So we can have each rule can be represented in a 27-digit number. So we can change it to bits. Like so we have a base 3 number and a vector in a 27-dimensional discrete space, right? So when we started the investigation on this multi-state solar automata, we made 1-bit mutations to the a 1-bit mutation corresponds to changing a single digit of the base 3 representation of the rule. So we have like the bits 27 rule with numbers and can be have 3 values, right? So we change one of the digits of the base rule that we used, and this is the base rule we used on the project. So since each digit has 2 alternatives, excluding its current value, there are exactly 54 possible 1-bit mutations for each rule we have and for the base rule we used. So this is like some of the 1-bit mutations. Actually, this is all the 1-bit mutations, out of the 54. And we also have the 2-bit mutations. This is a smaller sample of all the possibilities because there's a really huge jump between the possibilities of a 1-bit mutation, the 2-bit mutations, and also 3-bit mutations. So we made a visual analysis of this. The idea of the research is to give a good visual representation of the rule space. So it was really important to form initial hypotheses and also classify some patterns. So here we have the 1-bit mutations on the left, the center is the 2, and we also have the 2-bit mutations on the right. So we identified some behavioral classes, actually, including complex and also aperiodic dynamics, with some structure that persists between different rules and different bit mutations. We also use some distance measure to actually understand how different these rules are and how the behavior of these rules work, actually. And one of these distance was the Hamming distance that actually calculates like the difference between different bit configurations. So the more different bits they have between each rule, the more distance they are in this space. And this is kind of interesting because you may think that like the bigger the number of mutations you do on a rule, the more different it gets, and the bigger is the distance. But sometimes, like the 2-bit mutation, the 3-bit mutation, there's not much difference between them. And like when we do like 5-bit mutations and compare it to 4-bit mutations, there's also not much difference. So sometimes even if you have a bigger number of possibilities, it's still not much different because there's a structure inside the space of the solar automata. we identify some clusters when working on this. So we can observe that we have different colors here, and this is like the representation of 3 different clusters and the possibilities of it happening. Um, this is interesting because like each cluster is being constructed with the Hamming distance and also the feature between the visual exploration. So on the center, the center cluster, we have a specific solar automata representing it, and most of the solar automatas inside these clusters also have this structure. So, and different bit mutations produce almost the same exact results, which is kind of interesting. And we can also make the relation that the proximity in the rule space is also correlated to the similarity in the emergent behavior. So like we said, these different clusters have a lot of solar automatas with the same behavior inside them. And like the general conclusion, just to keep it simple, I guess, is like this is like a framework for understanding this rule space and the geometry and how each rule corresponds to each other, and we can see how different they are. We have on the article there's a lot of images that we can see, a lot of visual representations that are much better, and we can understand how these rules relate to each other. And this is really cool because it can help you to understand the complexity of a system. So some of the future work is like developing some metric sensitive to topological features, and also identify the boundaries and phase transitions to understand when a bit mutation can actually make the change to uh, uh, a persistent structure like the cirrus triangle or anything like that, because there's a lot of simple rules that they don't actually produce anything that is unexpected, but sometimes one bit mutation can actually give you something really complex. And I think this is the general idea. If anyone have any question, want to talk about anything, feel free. I hope I wasn't like too fast.
Thank you very much, Davi. We do have about 4 minutes left in the session, so we have our chat is open and our Q&A is open if anybody has anything that they'd like to ask. I will stay in until the end of the session and make sure that if anybody's got any questions or anything like that, that everything gets answered. Otherwise, that does wrap us up for today. I do really appreciate you guys presenting for us. Thanks so much for sharing what you guys worked on this summer and letting everybody kind of know a little bit of what we did at the summer school program. I know that I had a great time this summer, and we had a really, really successful program, a lot of really cool projects that were done. So I'm really glad that you guys were able to share. And I do hope that everybody who was able to come and observe and watch these presentations for us today got kind of a little hint of some of the things that go on during the course of that program.